Hello, everyone. Welcome to the Engineering Bar Show. This is the intermediate section of this this block. It is huge. It's very big. There's a lot to talk about. Almost too much. All right. So the topics we have today is the digital to analog converters. These are called DACs. This is a huge topic. I'm only going to cover just a very superficial amount. You could take. There's courses, and you can get a whole degree in this, a whole, but just in this topic alone, it's huge. So what is digital analog converter? We're going to talk about some basic formulas. We're going to talk about what device uses digital analog converters, how to evoke a digital analog object to your code. Okay. So the materials needed. This is a very simple section. All you need is a device, a Nucleo L476RG. This is just a device that has an analog out feature. There's a lot of devices that don't, so you might want to make sure before you go to Amazon or Digitech or whatever it is, DigiKey or something like that, that it has an analog out. How do you know? You're just going to have to look at the data sheet. Okay, you must have an oscilloscope. So if you don't have an oscilloscope, you can use an analog. I think it's called Analog Discovery. They have a oscilloscope. You're still paying, a good fortune for it. This is a digital scope, so this kind of has an output of it. And you must have a computer code. I assume you guys all have computers because you wouldn't be able to watching this on YouTube. But so I guess you could watch it on your phone. This code, this right here, when you look at it, you see analog in, and then you see one small word that says analog out, and it's hooked up to PA4. So that's how you know it goes to PA4. And that's the analog out. Okay, what is a digital analog converter? So basically, it's a digital analog, takes the binary and hexadecimal word from the microcontroller, converts it from a variable voltage from 0 to 3.3 volts at a frequency. So this is the ones coming in, the ones that are already in there. There's your digital analog converter is inside this chip. It then gets you don't really see it, or you could put it onto a scope. This is supposed to be like a speech waveform, and it goes out your speaker so you can actually hear it. So you're going to discover that there's other ways of getting a similar output like that. It's the pulse width modulation. That's coming up pretty soon, but right now we're just going to deal with just the analog out feature. Okay, so what are the design parameters? Okay, we're going to talk about this. Here we get into some little bit of algebra, little bit of maybe calculus. Maybe that's considered calculus. I'm not quite sure. All right. This is the voltage out. This is what you get. D is the binary word. The D can vary from 0x000 all the way to 0FFF. Okay. And the voltage R is your reference. Okay. And 2 to the N is the resolution. Okay. So the resolution is the higher the resolution, the more faithful it can produce that sound. So if you have a very high resolution rate, such in your monitor, you notice the pixels get smaller and it gets more tighter. The picture comes in better. If the resolution is not as fine, then the picture gets more blocky. So that's the best way. So the same thing with sound. The higher the resolution, the faithfully it can produce the sound, like of a dog barking or a music out of a guitar or something like that. So that is the same. That is what that means. The word is basically instead of just a byte, a word is just a set of instructions. So it could be 8-bit, 12-bit, 16-bit, 13-bit. I think sometimes our computers are like 64-bit words coming in. but this is a 12-bit. Well, no spoiler alert, but anyways. So this is your typical output of an 8-bit system. See how it's kind of like in these steps. In these steps, the 1/8 the step. It's 0, 0, 0, 2 eighths, 0, 0, 1, 3 eighths of the is 1, so on, so until you get to 1, 1, 1, and that's basically 8 bits. It's quite rough, but this is a very easy way of understanding that like a half of it is 4. What's 4? Let me think. Is 8. Okay. Or 0, 2, 4, excuse me. 4, that makes sense. It's 4. Okay. So here's the assignment by the EE manager. What is the resolution in your device? So it doesn't have to be my device. It could be whatever mbed. Hell, it could even be Arduino. Maybe you can check the Raspberry Pi. You're going to be disappointed about the Raspberry Pi, though. What's the reference voltage that we use or we're going to be using? And if I give you a word of 0xFF, what is going to be the output voltage? Here is what we're all waiting for. Design a device so the oscilloscope, it reads 0 volts, 1 volt, 2 volts, and 3.3 volts in a step-like fashion. So this should be not too hard, but we'll go ahead and go through it. So stop the video, design, code, and build. So if you got enough information, go ahead and do your own research of your own device. It should be analog out, but let's go ahead and move on. So the Nucleo L4RG, what I have, it says right around here. This is off of this. There's a lot of stuff. Here it is. Right here. 2 times 12-bit DAC, low power sample and hold. So there's 2 of them in there. I only know of 1, but right now there's 2 of them. 12 bits. So that's very important. And if I give you words 0FF, okay, and 4096, that's 2 to the 12 is 4096. Okay, and the reference is 3.3 volts will equal 3.3. That's the highest that I can do. So that's pretty easy, right? That's pretty much it. But so that's a constant. 0xFF could vary back and forth. So how do you initiate the analog out? The example is analog out, my out, PC4. And then this my out becomes the object. Okay, let's go to the code part. And yeah, let's go ahead and do it. Okay, so we're going to start. This is Code Talk. Thank you for watching. All right, so we say I put my name down. That's me. Use the analog function to generate 4 different voltages, but then we're going to check it out on the oscilloscope. That's pretty self-explanatory, so let's go ahead and do this. So we want analog. There, we see it does that. Okay, and we want my out. And what is it? It's PA4. That's right. PA4. Okay. We want a time. We don't want it too slow. Define time as 100,000. That is 100 milliseconds. Okay. And then let's go ahead and do some fancy stuff. So it's void gen v, let's just call it that. And what we want, we want this to be a float V. Okay. So basically it turns in there. So we want V, we want my out equals V divided by 3.3F with the semicolon. Okay. All right. So let's do, so it's pretty much what it is. So my out equals Gen V. Is it capital V? It is capital V, no kidding. Okay, and we want 0.00, or just 0. That's it. Oh, my bad. No, it's a bit weird. It's a function. Duh. And then we want time. Time. All right. So that's pretty much how it's going to go. Copy. Paste. And paste. We're going to change these. 1.0, 2.0, and this one's going to be 3.3 volts. Check over my notes real quick. I think that's it. I'm pretty sure that's it. Yep, that's it. Okay, let's go ahead and so far looks good. Let's see if we can compile it. Let's see my view. Let's see output. There you go. See all that? Look at all that. I'll see you at the proof section. Well, there you guys have it. There's the oscilloscope. Okay. And then you look down, and then there is the board, and that's it. That's all it is. Thank you. Please subscribe, and I'll see you next on the Engineering Bar Show.